Result of our little heart-to-heart, I think that this will quickly become a more beneficial activity for everyone, and we'll move more quickly, okay? So let's see what we can get done. We have a good solid 20 minutes, okay? So I think first I want to hit, because it will give us a mathematical breakdown of essentially what we're doing. So what I'm going to do is, instead of developing it necessarily, because this is not a physics course but an astronomy course, I'm not sure I want to break it down in terms of physics concepts. So if you're going to be taking an astronomy course, you're not taking astronomy for future astronomers, you're taking astronomy for non-math types. That's what this course is essentially. But I think it's a hybrid somewhere in there, because you guys are very bright, so I want to take advantage of that intelligence. So the mathematical law for universal gravitation can be summed up in a mathematical equation, consistent with what I said on the last video about what is gravity. Now, just because of this activity, people may understand this, but did Newton discover gravity? No. What's the big thing that Newton did? What's his?
The apple.
The apple. Thank you for reducing this to simply. He explained it. Yes, he quantified it. He kind of like.
The moon and like how it's not falling.
Alan, what did you say? Yeah, he discovered that gravity is not just the interaction between you and the earth relative to weight, or between you and a rock you're throwing. It's a universal concept relative to the entire universe. It's the same everywhere. The same everywhere. Understood? Let me give you a story. It may or may not be in the book, but I sometimes don't remember what is in the book, and I sometimes lose the ability to distinguish because I've been doing this for so long. But there's something called perturbations. Perturbations are, if something's orbiting, let's say here I have an object, and I have something orbiting like this, right? And all of a sudden, there's kind of like a wiggle or something. It's like, when it gets over there's this kind of like weirdness over here, okay? There's this, it's called a perturbation, kind of an irregularity in an orbital structure. Orbital structures are very mathematical. They can be predicted. You know, this is not predictable. This is random. It appears random to us. Okay, but these can also be used to identify things and predict things. So there's order in this apparent randomness. Yeah. Anyway, many years ago, they identified an outer planet called Uranus, and Uranus, sometimes pronounced Uranus, whatever. And the orbital structure, see, you have to understand something about astronomers. Astronomers simply look up at the sky a lot. That's all they do. That's their life. Some astronomers don't get out a lot. They don't get out much. I've known a few astronomers, and trust me, their personality reflects that. And so they would be looking at that was the outer planet, was Uranus. At one time, that was the outer planet. Okay? Okay, Amir, can you put those over on the side? I appreciate helping to organize the class. Appreciate that very much. So, but there were these perturbations in the orbital structure of Uranus, and they're wondering, what is that? Well, a bunch of astronomers got together and they realized, I'm giving you the short version of the story, okay? and realize that there must be a planet causing that. There must be a planet causing that, right? Okay. Well, there was a planet causing it. It's called Neptune. Neptune, that led to the discovery. When they figured that out, like that day, they found Neptune. Because they predicted where it was. They simply weren't looking. You know, when you're looking for asteroids in space, you know, the budget pays for like less than 1% of space. It's big. Space is big. You can't look every place at once. It's enormous, right? It's enormous. Think of space like this. If I'm looking at my finger, I can see people on the other side of the finger, but I can't make out, you know. Mr. Germany, raise your hand. Germany, Australia back there, see? Yeah, I can see him raise his hand, but I really can't. I know he's back there. But now let me look at the first person, first row, okay? Now I can see her. Can't really see the finger really well, but I know it's there. But I still can't see him. He's getting clearer. Now I'll look at Muhammad, next row. Now he's getting very clear. Now I know it's a guy, okay? Could have short hair, I guess, but now it's a guy. Okay. Now look at him, and my finger is still way out of focus. So think of it this way: when you look, right? When you look at something, you're literally in a giant bowl. You're in a sphere. You're inside a sphere, and when you look at an object, think of this. Think of sight as this. This will help a lot with space, a lot. Think of spheres inside of spheres. Boxes inside a box. I take a box out, I open it, there's a box in there. Take that box out, I open it, there's a box in there. Take it, right? So think of it this way. There's spheres, there's an infinite number of spheres. There's a sphere that has a radius of this marker. There's a sphere that has the radius of right here. I can see that sphere, I can focus on that sphere very difficultly, okay? I can focus on it, okay? I can focus on it. Now the sphere is like here, now it's here. Now there's a sphere that distance. Then there's a sphere back there. You see the fourth row, third row, right? That's a sphere. So I'm actually focusing on the wall of the sphere. So if I'm focusing on Uranus, the other sphere, which is literally millions of miles beyond that, is Neptune. If I'm not focusing there, if I'm focusing here or I'm focusing here, I'm not focusing in the middle. I don't see it. It's so far away, right? So unless I'm looking literally at the right spot, I can't see it. I don't know it's there. Unless you look. The light helps a lot. But there have been near misses of asteroids in Earth, and we didn't know it. We didn't even know they passed by until they passed by, because it's so big. So we use those perturbations to predict. How do you think we know there's planets orbiting stars hundreds of light years away? Because we can see perturbations. There was a scene in Star Wars, was it the Clone Wars, where the guy stole the data from the library, the Jedi library. Remember that? You remember that scene? And Anakin goes, was it Anakin and who was it that went in? It was Obi-Wan. Obi-Wan goes into the library and the librarian says, no, our databases are perfect. There's nothing there. There's no planet there. Because they're looking for the planet, right? Where they're building the clone army. Yeah. Or no, they're not building the clone army. They're building the Death Star. No, or they're doing something. What are they doing?
Building the clone army.
Yeah, clone army.
No, they're...
Yeah, because it's like the guy...
Oh, they're building the clone army where they went and it's all water? That's the planet they were looking for?
Yeah.
Okay, they're building clone army. Excellent, well done. Excellent. I'm not often corrected about Star Wars, but that was I am in the presence of greatness. I want you to know that. Okay, so how did they find that planet? Well, they looked at perturbations of the other planets that are orbiting that particular sun, and they found it. Remember? Do you remember? Well, the way they found the planet and knew there was a planet there, they looked at perturbations of the planets that are going around the same sun. So they said, wait a second, if there's perturbations here and there's perturbations here, so here you have the sun of that distant planet, okay, and you have these rings, right, these imaginary rings, and this has these perturbations, and this has these perturbations. Well, wait a second, the only way that you can have perturbations here and here is if there's a planet here.
Mr. Darcy, this excites me. You should make Star Wars connections more often.
Isn't that cool? So that's what they did. They found perturbations, right? So that's how they found it. You understand? It's important. So what's my point? Is there a point? Is this a giant tangent? Is Mr. Darcy developing early onset dementia or what? No. The idea is that the laws are universal. The law of universal gravitation. That word universal has deep, heavy meaning. The laws that we observe here are laws that are consistent throughout the universe. Perturbations in the orbital structure of Uranus, that planet in that galaxy far, far away, is also based on Newton's laws of universal gravitation. Exciting. Okay, so let's write down the law of universal gravitation. F equals m1 m2 over d squared. Am I missing something? That's it? Are you sure?
Put F grav, like for grav.
Isn't G, that's universal gravitational constants with the G in front.
You want to define what each
But if you
variable
just
is?
want its law of universal gravitation, you got it correct.
You want to define each variable?
Is that missing something? Yeah, you're right. So you know what? Let's do this. Let's do this. Can we do something? We'll go like this. What symbol do they use? Yeah, they use this.
Yeah.
What does that squiggle mean? You remember your mathematical functions? Anybody know what a function is? Okay. You don't know what a function is?
It
Yes.
means about, correct?
A function?
Like no, I mean the squiggle means like about.
Yeah, proportional, whatever. Okay, so in other words, if I take this, y equals mx, right? I have a bunch of things there, right? Right? I have m equals xy, okay? Yes? M is a constant. In other words, what happens to y relative to x? What happens to y relative to x? So let's solve for m. See, that's what you do. You solve for m or some constant, and you find out what it does. So you say, okay, so you say m equals y over x. Now, this is important. Everybody's listening, okay? This means that, you know what that means? I'm looking at that and I see what it means. Just the shape of it. It means that x is directly related to y. They're proportional to one another. And the definition of the relationship is linear. It's a straight line. How do you know that, Darcy? How do you know that? I mean, how do you know that? Well, I know that because, listen carefully to my words. The quotient constant, that's the constant, that's called a quotient. The quotient constant is always linear. If you have, what degree? What is the degree of the numerator and the denominator? What must it be? It has to be what? 1, right? In other words, the exponents are 1, right? Right? Yes? Okay. As opposed to squared, where it's parabolic or whatever, okay? Or how about this? That's a constant. What do I know? This is an indirect relationship. These are the two basic relationships that we use all the time in science. So this is indirect, right? This is indirect. That's a product constant. A product constant is indirect. In other words, let's test it. Let's test this one too. That has to remain m. Pick any number. It has to remain m. So let's say that's 1 over 1. So then if I'm going to make that a 2, I got to make that a 2. Right? Or let's say 6 over 2 is what? 3. So I'm going to multiply that by 10. What do I have to do with this? 10. So as this increases, what must that do? it has to increase, right? So that's direct, right? So as one increases, the other increases. That's called a proportional relationship. What happens when this increases? Let's say this is 10. So this is 1 times 1. 10 times 1 is 10, so that's 10. So I'm going to increase this 100. What do I have to do to this? I have to make it smaller, right? I have to decrease it. Let's say this is 1 and this is 1, let's say. So that equals 1. So I'll make that 10. What do I have to make that? 1/10. 100, 100th. 1 billion, 1 billionth. As one's increasing, the other's increasing, right? Well, how do I know, what's the relationship between mass and force? In terms of gravity, in terms of the force of gravity. In other words, here is two things. Is the force strong? No. Has it ever been measured? Oh yeah. Believe it or not, it's been measured. They measured it. Weird, huh? But they measured it, yeah? Is it strong? No, it's very weak. So let's see. Let's increase the mass. Earth and the moon. Now, is that force greater?
Yes.
Yeah. Well, do you predict that as true based on this? Do you predict that it's true, Aya? Do you? Well, look at this. As this number as this product becomes greater, as these masses become greater, 1, 1. Let's say this is 1, 1, 1, 1, 1 over 1 equals 1. 1. Right? Right? Okay. 1. This is 1, this is 1, this is 1. This is 1. Now we're going to test this. Okay. You make these each 10. 10 over 1, 10 over 1. That makes it 100. Right? So what's the relationship between mass and the force? It's going to be what? It's going to be direct, right? It's going to be proportional. Correct? Yes or no?
Yeah.
Okay. And what is the relationship between both of them together? It's exponential, right? It's exponential, isn't it? Because you're squaring it. This is like x and this is x. It could be the same, right? But it's not the same. But it can be exponential, right? Yeah? Right?
Yeah.
Could be parabolic, couldn't it? Could be. So what's the relationship between force and the distance between these two things? What's that? Is that indirect or direct? What's the relationship between the force and the distance? Mathematically, you don't have to understand the physics. Mathematically, what's the relationship? It's indirect, right? Matter of fact, it's inverse square, isn't it? All right. I heard these guys doing it. You were magnificent. I want you to know that, you two. Okay. You were explaining this like you were two Nobel Prize laureates in gravity, having a discussion over coffee in the morning. I was at my desk listening to these two. I felt like I was in the presence of greatness. I thought that I had to look up to make sure that there weren't two Nobel Prize laureates in the room. Okay? Now I'll put it on tape. Brianda and Samia. Unbelievable. You can show your children this tape. Okay?
I will.
All right? Okay. Now, so let's do it. 1, 1, 1, 1, 1, right? Okay? All right, okay. 2. 1/4 now, right? I doubled it, but this is quadrupled inverse, right? So inverse quadruple. Does that make sense? You get it? 10. 10 down here. 100th, right? Inverse square, right? You get it? All right, let's see. Half. 4. You get it? So what's the relationship between distance and force? Inverse square, right? What's the difference between the masses and the distance? Is what? It's direct. One goes up, the other goes up. Understood? You get it? You get it? Okay. So what do you have? You have what? You have masses you have distance, and you have force. I really finished the unit and we're about ready to stop. I've got like 2 minutes left. Perfect. Plenty of time. Didn't I do a good job? Thank you. That's very nice of you. And I have a clapper here. I mean, I'm sure that has nothing to do with the fact that I just wrote him a letter of recommendation. I would never think such a thing. Okay, good. So this, if I have 3 things that can change, 1, 2, 3, how do they, if I'm changing all of them at once,